We've now shown that whenever phi is an axiom of PA+, there is a deduction of phi in Z infinity. The last thing we need to do is show that if we prove something from the axioms of PA+, then it's also deducible in Z infinity. If you consider that a proof from the axioms of PA+ involves starting with the axioms and then applying the rules of first-order logic one by one, that amounts to saying that we want some sort of inductive argument that says if we can deduce some things in Z infinity, then anything that follows using one of the rules of first-order logic is also deducible in Z infinity. I can't fill in the details of that without writing down the rules of first-order logic, and it would be a bit of a digression to write down a formal system of first-order logic just to immediately embed it in Z infinity and then forget about it again. Really, I'd like to just hand-wave this away and say Z infinity looks a lot like ordinary first-order logic, so maybe we can just take for granted that we have these deductions, since at least we have the axioms. But the embedding of the quantifier rules is a little bit subtle, and importantly, it's actually the place where a key idea about how the bounds work is located. The definition of the bounds on deductions is really weaving between a few constraints, and one of those constraints is located in this proof, so we would miss out on something important if we didn't say something about it. So I'm going to sketch a few ideas from the proof. For the sake of this explanation, I'm going to assume that a proof from the axioms of PA+ is a finite sequence of formulas, say phi0, phi1 through phi n, so that each formula is either an axiom of PA+ or is justified from previous steps. This is the typical setup for what is called a Hilbert-style proof system, but if your preferred approach to first-order logic is natural deduction or something else, you might expect proofs to look a little different. Basically, what we might expect to show is, by induction on I, Z infinity deduces phi I with bounds f of I comma b for some function f to be determined later and some natural number b also to be determined later. And we would prove this by induction on I. So for each I, either phi I is an axiom, in which case we'd use one of those results we already proved, or phi I is justified from previous steps, from the phi j with j less than I, by a rule of first-order logic. And then for each of the rules of first-order logic, we need a case explaining how to translate that rule into Z infinity. And then this function f of I would come from counting the steps in each of those cases. The biggest bound from an axiom was omega times 4 plus 2 rank of phi plus 8, so we might hope f of I is going to be along the lines omega times 4 plus 2 rank of phi plus 8 plus 13 times I, where 13 happens to be the number of steps in the largest case, corresponding to one of the rules of first-order logic. This is almost what happens. If this were all that happened, we wouldn't be worrying about the details. I would have just hand-waved the whole thing away. There are two problems to deal with. The first is that first-order logic deals with formulas, not just sentences. So we can't always hope to deduce phi I in Z infinity, because phi I might be a formula with free variables. When you have a proof with a free variable in the conclusion, in a typical proof system for first-order logic, you prove something like x plus 2 equals 2 plus x with x free, and what you mean is you could replace x with any natural number. So when we prove from first-order logic x plus 2 equals 2 plus x, the corresponding deduction should be for any m we can deduce m plus 2 equals 2 plus m. So our actual inductive hypothesis should be more like, for each I, phi I is a formula with free variables, x1 through xd, and then Z infinity deduces phi I with x1 replaced by m1, x2 replaced by m2, and so on up to xd replaced by md, with bounds f of I comma b for any choice of natural numbers, m1 through md. So when we replace all the free variables with numbers so that we have a sentence, we can deduce that sentence. It's going to be important that the ordinal bound doesn't depend on the numbers we substitute. The numeric bound can, in fact, the numeric bound must. If you go through what happens with the for all introduction rule, the numeric bound should have the form the maximum of b together with m1 through md. That's one complication. Going through the details like I did in the notes will get you through the for all introduction rule. The second complication is on the exist side. Any proof system for first-order logic will have some kind of existential instantiation rule. A rule where you say, since I've proven this for a particular term t, there exists a t so that this is true. I'm going to assume it has the following form. From psi0 or psi1 with x replaced by t, conclude psi0 or there exists an x psi1. If you're wondering why there's a disjunction here, remember we're in negation normal form, so you might have seen a rule like this stated, from psi0 implies psi1 with x replaced by t, conclude psi0 implies there exists an x psi1. Again, different proof systems handle this in different ways, but this is a representative example. The relevant case in our inductive proof would say, suppose that phi I has the form psi0 or exists an x psi1, and there is some j less than I, so that phi j was psi0 or psi1 with x replaced by t. For the sake of minimizing notation, I'm going to assume that psi0 is a sentence, and that psi1 with x replaced by t has one additional free variable, which I will call y. This is enough to see everything that happens in the general case. Nothing new would happen if you had more free variables. The inductive hypothesis for j said, for each m, z infinity deduces psi0 or psi1 with x replaced by t and y replaced by m, with bound f of j together with the larger of b and m. And we need to prove that z infinity deduces psi0 or there exists an x psi1 with y replaced by m. If it's not already clear, the important thing here is the term t itself could contain the variable y. So the term t isn't describing a specific number, it's really describing a function of y. It's better to reverse the order of these substitutions. Taking psi1, which has two free variables, x and y, first replacing x with t and then y with m, is the same as first replacing y with m, and then replacing x with, well, not t, because t had y's in it that should be replaced by m's. So replacing x with t prime, where t prime is what we get when we replace y and t with m. So let's write psi1 prime for psi1 with y replaced by m. Then the inductive hypothesis gave us deductions of psi1 prime with x replaced by t prime, and our goal is to prove that z infinity deduces psi0 or there exists an x psi1 prime. Of course, we want to use the exists introduction rule. The problem is that psi1 prime is trapped in this disjunction, so we need to break apart the disjunction first. There's another of these common patterns for taking a disjunction and breaking it into the two separate sentences, and it uses the cut rule. So we can use this, and then we can use exists introduction, and then we can use that pattern we've seen before to take these two sentences and make a disjunction out of them. The thing to look closely at is the bounds on the exists rule. Remember, for the exists rule, we need t prime is the function t applied to the number m, to be at most h of the ordinal bound, h of f of I, of the numeric bound, which is the larger of b and m. So t, the original term, was a term in the language of arithmetic, so it was written using the function symbols in our language and the variable y. T might be y plus a million, or it might be gy cubed of y to the 15th. Some term of the Goodstein sequence, depending on y. It has to be the case that for every m, the value t of m is at most hf of I of the larger of b and m. Back when we described the language of arithmetic, I said it was harmless to add lots of function symbols, like the exponential and gx of y, but that we couldn't add the function symbol capital G of x, where capital G was the Goodstein function. And I said the difference between these is that g of x grew too fast. This step is why. We want the ordinal f of I to be less than epsilon 0, and the bounds for exists introduction say that means the terms in our language must represent functions which grow at rate below h alpha for an alpha less than epsilon 0. The term t had some function symbols in it. Each of them represents a function which doesn't grow too quickly, so we can pick an ordinal beta 0 less than epsilon 0, which is big enough. We take f of I to be beta 0 plus whatever additional stuff we need, and that's going to guarantee that the bounds for exists introduction work. Okay, that's enough on this. The notes go into a little bit more detail. The punchline is, when we put this all together, we get a theorem that says, if phi is a sentence provable from the axioms of PA+, there is an ordinal alpha less than epsilon 0, depending on this proof, and there's a natural number b, so that z infinity deduces phi with bounds alpha comma b.